Good evening, everyone. Just to let you know, we are recording the Zoom meeting today. Today, I am so privileged to introduce a stellar guest speaker who is inspirational in so many different ways. Miss Ezinne Uro-Okoro serves as the Assistant Director for Space Policy at the White House Office of Science and Technology Policy. Ms. Uro-Okoro determines the civil and commercial space priorities for President Biden's science advisor at the White House. She has worked with NASA for 17 years as an aerospace engineer, technical expert, manager, and executive. She has contributed over 60 missions and programs and has hands-on experience working across small satellite mission design, large spacecraft development, system engineering, and computer science. She holds a master's degree in system engineering from Johns Hopkins University, space robotics from MIT, and science and technology policy from Harvard University. She has a PhD in space systems for MIT on the robotic assembly of satellites. In addition, she founded Terraformers to grow affordable fresh food throughout the productive backyard gardens as a precursor to growing food in space. She's originally from Nigeria, and her immigration story is profiled in President George W. Bush's book, Out of Many, One. It is so exciting to meet such an overwhelmingly accomplished woman, such as Miss Ezinne Uro-Okoro. How lucky we are to have such a role model to speak to us today. On behalf of Girl Scouts, I welcome Miss Uro-Okoro to this event. The stage is all yours, Miss Ezinne.
Thank you, Mia. Thank you so much for that very kind introduction. Good afternoon and evening to all. It is such a delight to be here. My name is Ezinne Uro-Okoro. Ezinne rhymes with resume, attempts to help people remember it, and I'm just very delighted to be here with you all today. So I'm the Assistant Director for Space Policy at the White House Office of Science and Technology Policy. And I want to tell you a little bit about what that means first before we dive into robotics. So the White House has a number of offices within it, and they all help to provide the president and others within the White House, which is officially called the Executive Office of the President, with advice on scientific, engineering, and technological issues. We also help to lead the entire federal government, which we sometimes call the interagency on science and technology issues. We make sure that NASA is talking to NOAA. We make sure that federal agencies that regulate are talking to agencies that build spacecraft and build these robotic arms, for instance. And we serve as a source of scientific and technological analysis and judgment for the president with respect to all these major policies, plans, and programs within the federal government. So our mission really is to maximize the benefits of science and technology to advance health, prosperity, security, environmental equality, and justice for all Americans. So there are several people who do different things in my office, and I focus on space. Topics like space weather. Space weather is also called heliophysics, which is the study of the sun and the atmosphere around it. A solar probe, if you've heard of it, is one spacecraft that is studying the sun right now. I invite you to look up others. Microgravity research is another topic that I work on. And microgravity research really involves space research that's done in low Earth orbit. That is the distance around 400 to 600 kilometers from Earth. So that's where the International Space Station is housed right now. And some of you may have actually sent experiments to the space station if you've worked on scientific projects that have gone to space. I work on Earth observations. If you are passionate about climate, we use a lot of satellites, particularly in the low Earth orbit region that I mentioned, to not just predict precipitation and our weather, but also to help save lives. That was actually a program I was very proud to have worked on during my time at NASA. I worked on the Global Precipitation Measurement Mission, And till today, it still helps to predict hurricanes and save lives. And it's just an honor to be able to contribute to something so meaningful and impactful. I also work on orbital debris. So if you care about sustainability, if you care about space being free from clutter, we have a lot of junk in space, which we technically call debris. And we are looking for ways to ensure we track the debris so that it doesn't hit other spacecraft in space. We want to make sure that we can recycle the debris or repurpose it. Think of moving the debris, because we don't have a waste collection system in space. So we have to be able to manage the debris. And we also want to prevent new debris from going into space. And then there are topics like aeronautics and human exploration and space science. But I will focus my remarks on in-space servicing, assembly, and manufacturing, which is a topic that's very near and dear to my heart, because I spent years in school, as well as studying robotics. Now, the White House called me a card-carrying engineer to serve after 17 years of building spacecraft. I built 7 and managed teams and guided space missions. There are over 60 total at NASA. And I'm delighted to actually use this opportunity, not just to speak about robotics and in space manufacturing, what you can build, but I want to link how those tangible achievements really inspire us all and exercise our minds and improve our livelihoods. So if you remember one thing from this talk, I want you to remember that space is not only a powerful phenomenon that can fulfill your entire livelihood, but it's multidisciplinary. It can be used for multiple purposes here on Earth, and it serves almost every American. I'll give you one example before I dive into my main story. One example is the James Webb Space Telescope. Some of you may have seen the images, hopefully, last July. That falls under my activity. So I had the distinct pleasure of planning that event on behalf of the president for the reveal. And, you know, there are people who spent 20,000 people in total who spent decades working on either the micro shutters. Micro shutters are the little windows, and they made about a quarter of a million. There are 250,000 micro shutters that open up. They take all those images, and you know, you may never meet that person. You may know that person, but you may never meet, others may never meet that person who worked or that team who worked on the little cameras or the shutters that close and protect the cameras. And so it's just really important to realize how vast the contribution can be from multiple sources. So for my main story, I want you to imagine something. I want you to imagine a girl named Georgia. Let's say she's a kindergarten student, and she's learned 3 things this week at school. She's learned that she can build a satellite. She's learned that the satellite can fit in her backpack, and it's possible to control it with a robot when it launches into space. And in discussing all the tools that one can use in space, whether it's spacesuits for kittens to comfortable habitats that unicorns might live in on the lunar surface, you know, she understands that whether she becomes an engineer, a physicist, a filmmaker, a banker, a tailor, a farmer, a senator, an architect, or a roboticist, she can work in the same sector. She can help to contribute to space innovations that are often directly transferred here on Earth to improve our lives here. And over the past decade, the multidisciplinary uses of space have been incredibly clear to everyone, from young people like you to even people who lead finance companies on Wall Street, who usually don't seem to think about space. There are a lot of us here on Earth and in this country who are actually serviced by satellite technology through space communications, GPS, power grid monitoring, and there's a slew of businesses, whether it's weather monitoring satellites, gas stations in space, repairing and refueling satellite garages, for instance, that are springing up to supply the US government right now with our needs to ultimately benefit every American here on Earth. And there are new space companies that appear every day, and it just feels like the space age has really arrived. It's been arriving, but we just feel like it's here. Now, this is the point where I want to give you a little exercise, and I will collect results at the end. The exercise is, I want you to think as I'm speaking to you about how you would, the very first thing you would do, or one of the most critical things you would do if you were designing a robot that was either monitoring a weather satellite in space and had to fix something on the satellite that was broken, like let's say the battery was broken, or it was part of the gas station in space and was helping to refuel another satellite in space. I want you to think of the first thing or critical thing you will do to ensure that that robot has power. I want you to think about the energy source and how you will keep it operating 24 hours a day, or if you want it operating 12 hours a day, tell me why. So we will get to that at the end of the program. And I'll give you a taste of how we're going to go through answers. So at NASA, I told you I worked on several missions, and Mia mentioned, over 60 programs. And one way we run NASA programs is by what we call reviews. We call them either design reviews or requirement reviews. You basically have people who are not working on the project, but who are very knowledgeable about the subject, come and take a look at your work, and they give you feedback. And it's not like giving your teacher, your homework, and then they grade it, and then nobody else sees the grade except you and your parents. Everyone gives you feedback openly. So I will be giving you feedback openly on the brave souls who will give me ideas. And the reason that that's helpful is because everyone is learning when everyone hears the feedback. And it also helps because if you're the roboticist and your friend is a computer scientist and your friend helped write the code for the robot and you helped build the robot, the hardware itself, the computer scientist has to listen to the feedback you are getting on the robot so that they can also edit their code if they need to. So that's why everyone needs to hear it. It's not it's not done to shame anyone. And we usually try to break the system. We usually try to look for errors. So if you are, this will be a tip if you're considering whether you should be an engineer, but if you find yourself always finding, problems around the house or asking, why can't we do this? Why can't this be better? Then you are already an engineer, and I look forward to welcoming you into the field. Okay, so while that's at the back of your mind, let me go more into, in space servicing, assembly, and manufacturing, why that's important. So we think, we need to enhance the use of space innovations to improve life here. This includes servicing satellites. There are so many satellites in space. Right now, the statistic is about 90% that could extend their lifetime, that could work for much longer if they had more fuel. So imagine if 90% of cars on the road just couldn't move because they didn't have fuel. I mean, that would be a lot of, it's just taking up a lot of space, not to make a pun there, right? And this also affects space debris because we don't want to clutter things, just like we don't want to clutter highways of cars without fuel. So servicing satellites is important. Manufacturing and assembling things in space is important. Things like not just spacecraft, building it in space, but that would be cool. So I built things here on this planet, but I really look forward to you all building satellites in space with your robots. And, for manufacturing and assembly, you have to think of habitats where people will live. At first it will be robots, and well, it will be humans building those habitats, and then we will probably move to a hybrid of humans and robots building those systems. And then, I look forward to a time when it's just robots. You control them from here and you tell them to build you a home in space. And imagine using that technology to also build things here. So in space, servicing, assembly, and manufacturing really helps us tackle a lot of these challenges, like the refueling service that will help us refuel satellites similar to the way we refuel our cars. And the reason we don't want those satellites to run out of fuel is because they just float in space until they re-enter the atmosphere. But refueling, as I mentioned, allows them to continue providing scientific facts for whether it's climate research, whether it's exploring our universe longer than was possible. And that really helps to improve our management of our space program, so that we're spending less money on satellites because they can last for a long time and just be refueled. We recently learned that there's a technology where one satellite could act as a tug, meaning it could act as a satellite 1 minute, and then the next minute it could attach itself to another satellite and pull the other satellite to another location. So it could pull things, which means it could clean things up in space. And, that's the kind of technology that we want to advance when we think of in space servicing, assembly, and manufacturing. And so we put out a policy to help really encourage the commercial sector to continue to build more of these tools. We want to advance more research and development in these areas of robotics and autonomy and autonomous systems. We want to prioritize building large structures. So right now we have the International Space Station as the largest structure in space. So it's, almost 30 years old. It might be retiring soon. What will the next International Space Station look like? We hope that it's built by a commercial company, but it needs to be smarter, right? It needs to have more robotic components, more autonomy, and it needs to also help us as we, promote working internationally, collaborating with other countries, and providing sustainability to our environment in space. And it also needs to help us with ISAM innovation, with innovation to build more systems that are newer and smarter and can, for instance, let's say the new space station is able to dock any kind of satellite. Right now, that's not possible on the International Space Station. The International Space Station is a magical place because it was built, slowly, and astronauts installed it piece by piece. But the next space station will probably come together robotically. And it's important for us to understand robotic advancements, software advancements, advancements in cloud networks, and even ground-based communication. And also, one of my favorites, additive manufacturing. So this is the idea of using, composite materials to build anything, to print anything, whether it's a hammer or a spacecraft, a ladder, a car, or maybe even a rocket. There are companies working to print rockets using additive manufacturing. And why that technology can transfer to space is because there is, regolith in space, and there are companies looking into using regolith to manufacture in space. And, Hubble Space Telescope, just like other telescopes that we have in space, like James Webb that just launched, that brought us glorious visuals of the solar system. But Hubble is especially relevant in this case because it was visited 5 times by astronauts. And during each visit, they repaired and upgraded the telescope, thus making it last longer for a new generation to use. But we're moving into an era where Georgia and her satellite building skills, her robotic skills can not only build things here, but can build robots that would help to serve as mechanics in space and repair the next telescope. You know, JWST is the James Webb Space Telescope is about 100 million miles away, and we haven't sent humans that far. So if we were going to repair it, what would we do? The best thing to do would be to send a robot. And, you know, to give you a hint, you'd need, you know, solar power, you'd need to ensure that the robot is being kept cool enough so that it doesn't overheat. So that's what we call thermal considerations, keeping it cool when it needs to be cool, making sure that it can get warm enough when it needs to get warm to execute its tasks. And it would just be great to send a robot there and fix it rather than sending a human 100 miles away. And, you know, we are entering that era where you all, like Georgia, and your classmates can command and build this robot in space, just like you would any other school project. So I think that's really exciting. And that's the whole point of advancing innovation in space through advancing research and development in space servicing, assembly, and manufacturing, and in prioritizing building big things like space stations, and ensuring that we can apply those technologies not just back here, but also to the moon and to other celestial bodies like Mars. So the story of Georgia, who's, you know, learning how to build satellites, is not really common because there are lots of schools that don't have that technology. And we are moving into a time where that will be commonplace for all of you, or that will be commonplace in schools. And if there's anything that we can do to support it by, you know, inspiring the government and companies to build more of these innovative technologies, which will then require teachers to teach the skills that are needed to build these technologies, we are very interested in doing that, so that we can ensure that more people, more countries get their hands on technologies that they can send to space. And we get to move away from a time where it was just mostly countries that went to space or put things in space, or really wealthy companies. But we move into a time where you can build a robot in your home, make sure that it can last in space, and have the opportunity to send it up to space in a rocket, and have it do some good, have it really build something really impressive or fix something in space. So I'm gonna end with, you know, what you can do, or what is next in the coming years. In the coming years, we will see, I talked about refueling a lot because we will see a lot of that technology, because like I said, there's just lots of satellites that need to be refueled. And it's not just the arm that is needed. You have to think about everything that's needed to catch something that is just orbiting, floating by itself. You need what we call an interface for all intents and purposes to attach your arm or your tool to it. You need to find the location of the propulsion tank. You need to refuel it, be able to twist, you know, grapple it, twist, open, and refuel, and then close it properly. Make sure that it works. You know, your robot has to or your system that has a robot as part of it has to wait until someone on Earth tests that new that spacecraft to make sure that it can still work. And then there has to be an opportunity for you to obviously move your arm away from that robot safely before it can then move again. And make sure that both of you are not moving in the same direction at the same time so that there isn't a collision. And then your robot moves to another satellite to service. There are opportunities, as I mentioned, to service telescopes that are far away. There are opportunities to tug at satellites and pull things. There are opportunities to also clean up space, so it's not just acting as a mechanic, but also how do we create some kind of waste collection system autonomously in space? How do we build habitats? How do we even build greenhouses that might help astronauts grow food or help you when you go into space grow food? Who is your assistant when you are on the moon? Who is going to the far side of the moon for you? Who's driving? Can you just send the rover? And robotics obviously isn't just an arm. You could send the rover that you have to the other side of the moon, the far side of the moon, if there's another camp over there, to grab something, and then you control it and send some commands for it to come back to you. So there are just many opportunities for technologies within the next few years. And what is happening on orbit, as I mentioned, which is 400 to 600 kilometers above the Earth and that space. And what is going to happen on the moon is next. And then we will use those technologies to go even further, deeper into space, onto Mars. And I think that would be really, I hope to watch you all contribute to that in a very exciting way. Now, power is very difficult, and I'll give you an example of that. We've been trying to grow food in space for a long time, and we've been able to grow food inside the International Space Station. But think about it, it's not outside in space, just like you grow food outside in a garden or on a farm here, because the atmosphere is just so harsh. And one thing we're really hoping to get to is a point where a plant can grow by itself in a habitat for at least 14 days and enough for it to sprout to seed. Because once it sprouts to seed, guess what happens? You can grow that seed, grow the new seed, plant the new seed and grow it. And then you get more, and then you get more. And the problem with doing that successfully outside of the International Space Station, on the moon, for instance, is that the moon has two kinds of cycles. It's either really cold for 10 to 14 days, and then it gets really warm, just because of the way it orbits around the sun. And it's just difficult to get enough light, enough power to keep the plant alive for that long. So if we can't do that for a small plant, think of how difficult it will be to leave a robotic system, either in a rover or robot arms on the surface of the moon, without enough power, such that the LEDs are not charged, the solar arrays, the solar panels that it has are not charged enough, and then it doesn't work until it gets more sunlight. So that's a tough problem that we are looking to solve. And one of you may be the inventors of that in a few years, who knows? But, with that, I want to stop there so that we can start taking questions. And Gloria and Mia, what do you think about 10 minutes of questions before we start our design review?